So today we're going to do my absolute all-time favourite demonstration. This is iodine clock. Over all of the demonstrations, the colour changes, the explosions, this is without a doubt my favourite one. I will talk about that later. We're taking some of the skills that we've already learned and sort of combining it together. We're going to employ some really nice techers and make this absolute crowd-pleasing demonstration. Well, I like actually having lots of physical notes, so these are the notes from some of my favourite demonstrations. The recipe that I'm going to use today is actually pretty old, but I can't remember if I got this from the RSC or from a weird website called like Science is Cool or something. There are definitely some methods on the Royal Society of Chemistry website, but I'm just going to show you how I make mine. I'm very tempted to update this recipe at some point, but so far I've been doing this for 10 years. It looks really good. This is our main player in the reaction. This is potassium iodide, Ki. This recipe requires 50 grams of potassium iodide per litre, which is quite a lot. Thankfully, I'm scaling it down to 250, so we're going to do 50 grams per litre, so that is going to be 12.5 grams per 250. I always have these little square scraps of paper lying around in my lab, and they're really good for making lots of solutions. We're going to be making two kind of mixtures today, two solutions. One of them is going to be lots of solids dissolved into a solution, and then the other one will be liquids. And I will go into the science of what's happening in terms of the chemistry, but right now we're just going to do the sort of bare bones of putting it together. We've done Ki, now we're going to do starch. So we're using starch as an indicator to indicate the presence of liberated iodine, elemental iodine. This recipe calls for 0.2 grams for every litre, so we're going to drop that down. So 500 ml would be 0.1, and so 250 ml would be 0.05. It's going to be tough to weigh out, but it will be fine. Our balances go down to 2 decimal places. The main ones that we use in the lab, we do have some ones that go down to 5 decimal places, but we tend to only ever use those in very specific A-level chemistry ones. We will be able to weigh out 0.05 grams of starch though. The next up is our sodium acetate. I'm going to be using anhydrous sodium acetate for this, but you can use hydrated and you just have to adjust accordingly. It's going to be part of our buffering system, which is going to keep our hydrogen ions available to be able to supply hydrogen ions to the reaction. We're doing 4.1 grams for every litre. So 250 ml will half it and half it again. 1/4 of 4.1 grams is going to be 1.025 Gs for every 250 ml. I'm going to be pairing that with acetic acid to make our buffering system. So it's going to be an acetate buffering system. But that will be for the other solution, solution B. And so the last powder we're going to need is sodium thiosulfate. We use sodium thiosulfate mainly in these quite large pellets, so it can be quite hard to weigh out. I mean, I'll show you how to do that later. Our sodium thiosulfate is going to be pentahydrate, so that's 5 water. Didn't realise, but historically used to be known as hyposulfite of soda. So typically 9.4 grams in a litre. We're going to half it and half it again. So this chemical is what's going to give us the time delay on our reaction, so we need to make sure that we do this correctly. You can adjust this to do all of those crazy variations where you see people kind of point at it and it turn, or they go one after the other all in succession. Okay, so that's all the powders. Let's just have a quick look at our liquids now. Okay, so we got acetic acid here. Acetic acid is a weak acid, but it absolutely stinks to high heaven, so I'm going to use this in the fume hood. And then the other part of our liquid component is going to be hydrogen peroxide. This also has got to be fresh, or as fresh as possible. It degrades over time, and if your timing's all off, it's probably going to be the peroxide that's the issue. Before I start decanting our liquids, I'll just get everything on the stirrer. We're going to need the heater as well, because we're starting with a starch solution. I've already made a video on how to make starch. So hot plate on, get that nice and hot, nice thick-walled beaker over there, and then we're also going to need a watch glass for the top of that. The watch glass is optional, but it just keeps the heat in, stops evaporation. I mean, I've said this before, there's loads of different ways of making starch solution, but this is the way that I was taught. Heat-proof mat, so I'm prepared for when I want to take it off the heat. Now the starch is going to react with the iodine as the iodine's formed and give us that really nice deep blue-black colour. A nice little demonstration if you're doing introductions to enzymes and using starch as the indicator for a starch amylase reaction. But actually I have a little tweak on this reaction and the starch amylase reaction, which I'll show you at some point, which is a bit more relevant to what they're learning when they're doing biology. So weighing boat on, and then I'm going to tear the balance. Don't need a lot of starch really because I'm only making 250 ml. Normally I make a litre or 500 ml. Target weight here is 0.05, so it's really not a lot. And seeing as the starch has only been used as an indicator for this one, I don't think it matters too much about being perfectly spot on. The starch goes into the thick-walled beaker with a minimal amount of water. We're aiming to form a kind of a thin slurry of starch and water, and then as we heat it, that'll go clear. We can top it up with a bit of water, and then we can start adding the rest of our powders. Forgot about the watch glass, but we'll ignore that. Being pretty generous with the rinsing as well because we're using so little starch. I want to try and make sure I get every single grain of starch onto there. Such a small mass of powder, it's really hard to actually see it in there, but it is in there. So that goes onto the hot plate now, and I don't really want to do too much else while that's heating. I really don't want to get distracted and let that burn. Just want to get past the initial heating while the solution is quite thin. And then once we've topped up with a bit of water, we'll be fine to let that go. Just while I'm waiting, I'm just going to organise my life a little bit. These are the powders that I've got to weigh next. Okay, so now that the initial part of the solution has gone clear, I can just start adding a bit of water just to bring up the volume. That way I can definitely leave it on the stirrer and be safe. Rinsing down the sides of the beaker just to make sure every little bit of starch is in there. Watch glass goes on the top, and then we're just going to bring that up to temperature now. We're looking for about 70 to 90 degrees. Make sure all the granules are hydrated and just that everything is definitely soluble. So we'll do the rest of our powders, but I'll just take the beaker off the heater. Let that cool down. So I'm going to add some water now. Now that's on the heat-proof mat to let that cool down. Being fairly generous with the water because I'm going to try and dissolve more powders in there. Okay, sodium acetate now. That's going to be part of our buffering system, working in conjunction with the acetic acid. We need hydrogen ions in our solution, so we need to keep everything acidic. I have seen recipes that use sulfuric acid instead. I will go into exactly why we need those hydrogen ions a little bit later. Okay, so that's our acetate done. Let's add that into the solution, dropping it in from the weighing boat with plenty of rinses. And now that we're adding powders into the solution, we can start a little bit of stirring on the magnetic stirrer. So I'll just grab myself a stir bar and pop that in there. So iodine clock is really versatile. We can use it for if we're teaching kinetics, if we're teaching the starch iodine reaction in biology or in chemistry. I really enjoy doing a hot and a cold one if we're doing rates of reaction and effective temperature. You can also do a really nice effective concentration, which we'll go into later. There's a really nice tweak on this reaction in A-level chemistry where students adjust the amount of potassium iodide in the solution to change the timing. So many other topics this could be used for. Very, very versatile. Intro to chemical reactions as well. I really like if I have some solution left over, I'll use this one. So yeah, there are lots of pros for using this one in your lessons, but all in all, it's the absolute wow factor of that colour change. Now, next up, we've got sodium thiosulfate, and I like to use forceps for this one because we've got a very coarse crystal. And so it's been crystallising into these small oblong shapes, and it tends to be easier, especially when you're doing small quantities like this, to use forceps, and then right as you get towards the final mass, I'll just select and swap out different size crystals until I get to the mass that I'm after. And you can buy sodium thiosulfate as a much finer crystal that's easier to weigh, but I actually like using this really coarse crystal for a different demonstration that's for when we're teaching amylase, iodine and starch. The target here was 2.35, so I'm 0.01 under, but I'm not too fussed about it. These are pickling mason jars. They get a really nice tight seal on the lid, so I use these for my bench chemicals. So we'll add that in with a little bit of water and stirring, and then we'll get onto the big boy. That coarse pellet is really easy to throw in. And so now we're done with our sodium thiosulfate, so it's time to do our potassium iodide, our Ki. So the price of potassium iodide has gone up astronomically since I started. I know that the price of all chemicals have gone up since for the last 10 years, but potassium iodide in particular has just gone up astronomically for a chemical that is part of our bread and butter at school. Very, very annoying, very frustrating, especially when you're using so much for one demonstration. So try and get the most out of this demonstration, try and use it as much as we can. Lots of really great uses for Ki, lots of really cool displacement reactions you can do with halogens as iodine as the indicator for that reaction. Obviously elephant's toothpaste, another classic, using potassium iodide as a catalyst for decomposition of hydrogen peroxide. Oh, and that's the last of our powders now. So all we're going to do is add that into the solution. We're going to add a little bit more water just to make sure there's a bit of room for everything to dissolve in, especially this one. This is the biggest mass that we're going to be dissolving into this solution. Once we've done that and we've rinsed our weighing boat dry, we can start working on our liquid component of this reaction. Just being mindful of that final volume at 250. Just want to make sure that we don't overfill it with the water and make sure we leave enough room to top up to the line when we're ready. Alright, so just time for a quick clear up and then we'll get to the liquids. Okay, so the calculations for the liquids, we're only actually going to use 2 reagents and then we're going to dissolve those 2 in water, and that's going to be our final solution. So the first one is hydrogen peroxide, H2O2, and 30 ml of concentrated acetic acid. The thing with hydrogen peroxide is it's slightly different to how you buy a lot of your other liquid reagents, in that you don't really buy it as concentrated. You buy it in vol. So the vol is short for volume, and in this context, vol is an indication as to how much oxygen the hydrogen peroxide can release. It's normally sold as diluted rather than concentrated. It's highly oxidizing and highly corrosive, so it's a little bit safer to use and handle. Working this dilution is going to be slightly more annoying because the original protocol called for 500 ml of 20 volt peroxide and then 30 ml of acetic acid, and we need to adjust the volumes, but we need to keep the concentration the same. We buy the peroxide in at 100 volt, which is 30%. If you want to make 1 litre of 20 volt peroxide, you would take 200 ml of 100 volt peroxide, and then you would dilute that down with 800 ml of water. That's going to give you your 20 volt. And just keeping in mind that the original protocol was 500 ml of 20 volt peroxide. You used to halve that 1 litre 3 times, once for the original recipe and 2 more times for our 250 ml iodine clock. So let's half that and half it again. So it's going to be 50 ml of peroxide to 200 ml of water. So let's halve that one more time, and then that is our final volume that we'll add into our solution. So that's going to be 25 ml plus the 100 ml of water to bring that up to 20 volt. That's 125 ml of 20 volt peroxide. Now, classically, I forgot to hit record when I was doing my acetic acid calculations. You can kind of see them here on the right-hand side. Basically, the original recipe called for 30 ml of acetic acid. So all you do is halve that and halve that again. So that's 15, then that's 7.5. So we just need a small pipette to be able to pipette out 7.5 ml of concentrated acetic acid. Then you bring that final solution up to 250 ml with water. I'll pop these fillers onto these pipettes and we'll take it over to the fume hood and we'll just dispense everything in the fume hood. I'm going to make it up in this clear 250ml volley, and then I'm going to dispense it into a brown glass container. You want amber glass to be able to stop the hydrogen peroxide from decomposing as quickly. Acid to water, never water to acid. I'm not sure if it's the same for peroxide, but we'll add 1 to 2/3 of the final volume anyway into this volumetric of the water, and then we'll start dispensing our liquids into it. So we use these new style kind of plastic fillers at school. Wheezy bulb fillers are so much better, but the kids find it really difficult to use, and also it won't come up in their exam. Although these fillers, they do find them really, really difficult to use. It's very hard to keep the vacuum like consistent in there. I'm not too bad with them because I've had lots of practice, but for students only doing it once or twice in their life, it can be really, really difficult. So the bottom of the meniscus sits on the line. I can't count how many times I've said that in my life. Particularly with these fillers, you just got to slowly lift them up, try and get your volumetric or whatever you're pipetting into really, really close to the lid of whatever you're dispensing out of. So nice and slowly, just like that. That goes into the volumetric, and then we'll just dispense that out. The old hip click of the pipette there. Pop the lid back on the peroxide just while that's dispensing, and then leave the little bead of peroxide in the end of the pipette tip. Pipette goes straight into the fume hood sink because that's where all of the ones with the conc acids and anything that we use in the fume hood, they just go straight in there for washing up later. Now we just give it a quick mix up, and now we're going to do our acetic acid. Acetic acid is just concentrated vinegar, okay? But it is definitely strong enough to give your nose a real wake up if you use it, if you're leaning over it outside of the fume hood. So just for everyone's sake in the lab as well, I'm just going to use it in the fume hood. So we'll just draw up 7.5 mil, drop that into the volumetric flask, and then we are good to go. And that is pretty much it. We'll pop the lid on that acetic acid, and then we're just going to top up the volumetric flask with water to the line. Give everything a good mix so we're all homogeneous and evenly distributed. Final top up to the line at eye level. We'll do our 10 inverts, and then we'll look at the chemistry behind it. But just before we do that, we'll just finish off decanting everything for storage. So we get our brown glass for this solution that has got hydrogen peroxide in it. And then back to our first solution, grab the stir bar, nearly. Grab the stir bar out and give it a little rinse. And then we're just going to make sure that that's definitely at the line there. And then just decant that into a Durant. So let's give it a test and then look at some chemistry. So the full reaction is quite complicated for your average GCSE student, probably more better suited for A-level chemistry or triple science chemistry. This is from AQA A-level chemistry, slightly different setup, but the same reaction. Because you've got your hydrogen peroxide reacting with the iodide ion from the Ki that's been dissolved in. We've got 2 hydrogen ions as well from our buffering system. Now, as the iodine is being made, it is reacting with the thiosulfate ion from the sodium thiosulfate to make the iodide ion and the tetrafionate ion. That iodide ion goes back round to the top as if it's in a circle. So these 2 reactions are going on at the same time. So that top reaction is the slow reaction. That's happening all the time. The bottom one is the fast reaction. Once thiosulfate reaction continues on until it's all used up, and then you get that instant black colour. Such a beautiful and simple and elegant reaction. Chemistry doesn't always have to be crash, bang, whiz to be thought-provoking. When you're setting up the demonstration, you're going to want a white tile or some white surface just to give it that nice contrast. Obviously, that's a must for any colour change reaction when you're demonstrating. I've also seen people put it on a stirrer. I've also seen people decant it from flask to flask until it changes mid-pour. That doesn't always happen, but sometimes you can get it to change as you're pouring it, which is quite a nice a variation on that. If I'm demonstrating, I'll just kind of roughly eyeball 50 ml of each. I like to do one good swirl and then just let it stand. Don't take your eyes off it. Deep blue-black colour is from all that potassium iodide that we dissolved in, so it is critical to dissolve quite a lot of potassium iodide. I have seen variations where you use less, but it kind of goes to, it's just not as, it's not as striking. You could probably leave it out for a little while, but realistically that wants to go in the fume hood as soon as possible. You are actually going to be liberating iodine gas because of all the potassium iodide you've dissolved in. Hopefully we'll see some of that in a bit. Just going to show you some spent solutions, some old iodine clocks. Got some mould growth from the starch in our dissolved solid solution. And our hydrogen peroxide from our liquid solution is probably partly decomposed into water now. Shelf life of the solutions is probably a couple of days, but honestly, it always looks worse as the days go on. You want to make it fresh for the best results. Also keep the timing pretty spot on if you do want to try the old point and change variation, but that is really, really hard. You've got to be quite brave for that. Kind of cool, I guess, but not as striking. You can see the starch has been eaten up already, so you're just getting iodine being formed now. Okay, so now we're going to look at timing. So let's get a new conical flask and let's go again. This will be more for an investigation or a practical if you want to look at rates or if you want to look at rate order. Using these ridiculously oversized stop clocks. Much better than stopwatches though, they are completely bulletproof. Okay, so again, 50 ml of each. 50 ml of solution A. Eyeballing it. Solution B ready to go. And add, swirl, and start. A little slow off the mark, but pretty much spot on. 10 seconds exactly. Never ceases to amaze me how spot on this reaction is. It will change with ambient temperature. Obviously, it would be nice if I had a measuring cylinder as well. I often do this as a demonstration where I pre-warm or pre-chill solution A and B for rates for effective temperature. That will change how long it takes to turn colour, but now we're going to do a nice little tweak on this demonstration, on this practical. We're just going to add a couple of pellets of sodium thiosulfate. Just add 2 there, and then I've just got to dissolve that in. So that's going into solution A. So now we're increasing the concentration of sodium thiosulfate. More thiosulfate ions means that fast reaction is going to occur longer. So that the delay is going to be longer. I've probably doubled the amount of thiosulfate that I originally dissolved. Just going to have to make sure that is definitely dissolved in. In the A-level chemistry example that we were looking at, they're actually changing the concentration of Ki, but I quite like to change the concentration of thiosulfate. If I'm demonstrating to GCSE, just add a couple of pellets in. Okay, so I think we're good to go now. Bumped up the concentration of thiosulfate. So in we go and start. That's about 20 seconds on there, which is pretty spot on. I mean, I do know that my consistency between runs and my swirling wasn't exactly perfect. But still, a really, really nice tweak on this reaction here. Let's just finish up with disposal. We've got sodium thiosulfate again, and we're just going to put that in excess, basically. We are going to do that slowly. And then we're just going to stir it out. What you'll find is that it might go clear. So if I give it a real good stir and get some of that to dissolve in, it should begin to go clear. And then what will happen is on standing, that will go back to being brown or black. What I've done on that flask on the left is I've put a little wad of paper just in the neck, so you can kind of see that's being stained from the iodine fumes that are coming off. You can actually see the purple iodine gas coming off the solution where we've dissolved so much Ki in there as well, so it's really important to do this in the fume hood. You find that with the spent solutions and with solutions that have been sitting there for about 24 hours, on the addition of thiosulfate, you'll get this fizzing. So I'm not quite sure what that is. Maybe it's site of nucleation for the peroxide. If anyone knows, do let me know. But yeah, you'll get this fizzing coming on the addition of thiosulfate with the older stuff. So it's better to just get rid of it straight away. The thiosulfate, as you add it, it will take a while to dissolve. Once it's all dissolved, the solution will go back to being black. Then you have to add more, dissolve that down, let it go clear. Once that's dissolved and it goes black again, you keep doing that back and forth until it stays clear. Then it's good to go down with lots of water. Another option you can use is sodium carbonate. I really don't like using sodium carbonate, but I'm just going to show you what happens. It will basically react with the acid and you get crazy fizzing. What you really don't want is your fume hood filled with iodine water from it fizzing over. I can tell you that from experience. With really large batches, if we've done this multiple times, then what I'll do is I'll just put it on a stir on a really big beaker. And I'll just constantly add thiosulfate as the day goes on while it's stirring. This is carbonate solution, so same thing, probably a bit more controlled, 1 molar carbonate, but still, you're still going to get that fizzing from that acid-base reaction. And again, the final step is down the foul drain with plenty of water. Yeah, and that's it. So if you're still here at the very end of the video, thank you so much. This video was a real labour of love. I've said it before and I've said it again. This is my absolute favourite reaction of all time and I really want to do it justice. I would have loved to have gone into the history, why it's called the Landolt reaction, some of the tweaks with oscillating reactions that you can do. So yeah, if you like this video, just give me a like or a follow. That would be amazing. Check out the RSC resources and check out the periodic table of videos video and iodine clock. That video is absolutely amazing and I will see you guys in the next one. Thanks so much. Laters.